Const is a C++ keyword, and as the keyword it's spelled with a lowercase c. It means that you promise you won't change a value. That might be because you simply want to impose a little rigor on yourself, or it might be that you're being given a value that you're not allowed to change and you have to promise that you won't. So you can declare a local variable like this, const int 0 equals 0. And any code that tries to set 0 to 10 or minus 3 will trigger a compiler error. It's not allowed to be changed. You can take a function. Foo here can take a const integer I. That's a semi-pointless thing to do, right? Because I here is being passed by value, and any changes you make, you'll only be changing inside foo, and who cares, because they'll be thrown away when foo goes out of scope. But the second line, something, takes a const person reference p. And we've said a couple times, when you pass something by reference, someone can reach through the reference and change the value back in the calling code. Taking a const reference says, actually, I won't. It means I'm taking this by reference because the cost of a copy might be expensive. You know, when you take a function parameter by value, that integer or that person or that insurance policy or whatever is copied into a temporary that's given to the function, and that may be a very expensive copy. Passing by reference prevents the copy, but it enables someone to change the real object back in the calling code. And if you don't want that, then you write const person reference p. What will happen now is when the compiler compiles something, if any code in it changes p, you'll get a compiler error. So it's a very safe way to say, I'm giving you a reference to spare the copy, but this doesn't mean that you can actually make changes back in my code. Imagine that I take that person p as a const reference and I call some member function on it, like getName or getNumber. Unless the compiler knows that those member functions don't change any of the member variables of person, it won't allow you to make the function call. You have to give it that reassurance, and you do that this way. This says that the getName function won't change any of the member variables of the class. That makes them safe to call on a const reference. So if we have a const person or a const person reference or whatever called p, and we want to call p.getName, that's safe to do as long as the compiler knows that getName is a const function. That won't change any of the member variables of p. As you can imagine, getting all your consts lined up can be a challenge. It's called const correctness. So if our function something takes a const person reference and the code for something calls p.getName, getName has to be const. Well, getName's really simple. You've met person in lots of these demos. You know that all it does is return the first name and the last name tag together. But what if it called another member function? Well, then that member function would have to have const on it. And some of the functions may take parameters that need to be labeled as const whatever reference to make sure they're not getting changed. If you leave const correctness till the end of your development, it can just drive you crazy. But if you do it as you're writing, it can actually be a supportive framework that helps you to write higher quality code. Here I have an ordinary console application. I'm using the person class once again, and I've also declared a little function here up above the main. Let's take a look at what the main does. Starts really simple. I make a local integer called I, then I make a constant integer called ci. They both happen to have the same value in them. I'm allowed to change the value of I, but if I try to change the value of ci, I get wigglies. Error. Expression must be a modifiable L value. Const variables aren't modifiable, so modifying them gets you an error message. Let's take a look at this function double it. Right now it takes its parameter by value. Let's change it so that it takes its parameter by reference. This causes an error here. Why? Because 10 is not modifiable. If I have code in here that, I don't know, makes x 4, that's allowed, and it would change what was passed to it. So here, when we called it with j, it would change j, and in here it would try to change the 10, which is just weird. Now, there's no particular reason to take an integer by reference. The cost of copying an integer is not important. But many people are in the habit of taking things by reference, just it's a habit and they do it. When you take something by reference, then you should try to take it by const reference. Now, making that change makes this line happy, but now you notice it's made this line unhappy. And this unhappiness here is, well, what are you doing? It must be modifiable, right? Because once you've said it's a const reference, you can't change it. Let's take that away. Now we have generally a happy compiler. Anytime you're going to write a function that takes something by reference, and you might pass a literal like 10 to it, it needs to take it by a const reference. That's what you saw in the template. We had const tref. We take those things by reference because operators should take their parameters by reference for a variety of reasons. And if you're going to pass literal constants like 33 and 44, then it has to be a const reference. Now I've got some code that's going to work with objects. I have a person object called Kate, and I can call set number on that. And then I have a const person called ckate, and I have some commented out code that's going to try to talk to it. Let's uncomment this one. Trying to call set number. Let's see, I get an error message, and it's not quite as good as the error message when you were trying to change the value of a constant int, but the object has type qualifiers that are not compatible with the member function. It's a constant. I'm trying to set its number. That's a bad thing. You know what? If I uncomment this line, I also get an error here. Same thing. Type qualifiers that are not compatible with the member function. We look at getNumber and we're like, that doesn't change any member variables. Let's take a look at the definition of it. Yeah, it just returns number. It doesn't change anything. How could this possibly be a problem? Well, here's the deal. When the compiler has this line to process, it doesn't go and look at all the code for getNumber. In fact, it doesn't have access to all the code for getNumber in some cases, right? That may be off in some CPP. For the particular case of person, the code is in line in the header file, but you can't count on that. And even if it was available, it's not a good use of the compiler's time to be rooting through your code to look and see if it changes any member variables. Instead, the way that you say this function doesn't change any member variables is you put the word const in your declaration. Now notice if I put const here, I have to build in order to get my header file parsed, but I'll get errors. Specifically here, arbitrary number cannot be modified because it is being accessed through a const object. So by saying that set number was const, now my code won't compile because, you know what, set number is not a const function of person. It changes a member variable of person. So the compiler won't let you lie here. So take that away. The compiler will let me say that getNumber is const. It will also let me say that getName is const. And when you have something declared in the CPP, you need to put the const in both places here. So now getName is const because I put it in both places. GetNumber is only in the header, so I only need to put it there. SetNumber isn't const. It changes member variables of person. And if you look down the rest of these operators, you can probably also put some const correctness in here relatively simply. You know that the operator less than doesn't change the person that you're comparing to and doesn't change this person either. This is not by reference, so it's harmless, but we'll put that it doesn't change this. And the friend, the free function, can't have a const modifier out here because it's a free function. It doesn't have access to member variables of person, but I can say that it takes a const ref. And then for it's a free function. It doesn't have access to member variables of person, but I can say that it takes a const ref. And then for those that are implemented here in the CPP, while they don't match, I'll get warnings saying, I don't know why you're telling me about the operator less than that takes a person reference. As far as I know, you don't have one of those. It's true, I only have an operator less than that takes a const person reference. I also need to add this here that it doesn't change it any of the member variables of the class. And here. And this isn't a member function, so I wouldn't put the const out on the end there. I have red wigglies here. They tell me that I'm not allowed to access arbitrary number. It's a little confusing because didn't we make it a friend? No, we made this one a friend. Now that one's a friend. If you think as you go to write the function do I change the things I'm passed? I'm taking them by reference. Immediately put that const in there. You don't have to go through this process of fixing it up afterwards. So let's go back now. Notice we have red wigglies under the call to set number, but not to get number. And that's really what you would expect. Get number doesn't change the person. It's a perfectly safe thing to call on a const person. Set number does, and no amount of adding the word const is going to fix that. In fact, when we tried making set number a const function, you can use the const keyword when you're declaring pointers too, and it has two different possible meanings. First, you can declare that the pointer is a constant pointer. This means it can't be changed to point somewhere else. So in the first pointer demo, the PA pointer suddenly started pointing at B instead. A constant pointer can't. Or you can say that it's pointing to something const. Then star CPI is const. And you can't say star CPI equals 7. You can't use the pointer to change the value of that const integer. As you can imagine, if you take the address of a const integer, you better put it in a const integer pointer saying, I'm pointing to something const. Of course, you can do both if you want. This syntax declares a pointer that you cannot change to point somewhere else, and nor can you go through the pointer to change the value of what it's pointing at. I've called it crazy because it sounds like there'd be nothing for it, but you can use it to get values and to invoke const functions, which may be enough for you. I'll just quickly show you the error messages that you get when you declare constant pointers or pointers to constant things and then break your own rules. Here I have some code that works with the const and non-const objects that we already have kicking around. This is an integer pointer pi, that's the address of I, no problem. But if I uncomment this line, if I try to take the address of that const I, a value of type const integer pointer can't be used to initialize an entity of type integer pointer. And in other words, if I want to do that, get that address of CI, I have to put it in a const integer pointer. Here, I'm going to make a person pointer, address of this person up here, that's fine, and another local person, and then I'm going to try to make some pointers. So if I make a const integer pointer, that is a pointer to a const int called PCI, I can point that to the same place that this PI is pointing, in other words, the same non-const I under the covers, but because I've said that it's a pointer to a const, if I then try to go through it and do things, expression must be a modifiable L value. The compiler doesn't try to follow back the chain and so on. I said PCI was a pointer to a const. Then I tried to use it to change the value. What am I doing? And I get an error message. Notice, however, that I can change the pointer itself, PCI, to now point to a completely different local variable, J, that's sitting up here and is a non-const integer. Can take the address of that, put it in PCI, not a problem. I'm allowed to change where the pointer points to. Here the word const has moved away from the type and closer to the pointer. This is a constant pointer, so I can use it, star CPI, reach out through the contents and change where it points to the value 4, which means that I is, among other things, going to change to 4. But this line of code that tries to get it to point to J instead, expression must be a modifiable L value. I'm not allowed to change the value of CPI, not the value that it when it's stored through it when I go star CPI, but the actual value in CPI, the address, not allowed to change it. Now here's this crazy one, constant pointer to a constant int, and I can't do either of these things. So I can't reach out through the pointer, must be a modifiable L value, and can't try to get it to point somewhere else. I can use it. I can say int k is equal to the contents of crazy. So it's not completely worthless. I just can't change either where it's pointing to or the value contained in what it's pointing to. And that's the story of const So far, the only variables you've seen in all these little sample applications have been local variables, what we sometimes call being on the stack and having stack semantics. They go out of scope when the function ends. In fact, they go out of scope when they hit a brace bracket. So if you have an if, and then you declare some integer I inside the brace brackets of the if, do some calculations, then you hit the close brace bracket of the if, the I actually goes out of scope. That's not always what you want. Sometimes you actually want variables that have a longer life than that. And in C++, those variables live in what we call the free store. A small aside, many people use the word stack for local variables and heap for the free store. And if you go to a computer science textbook and look them up, stack and heap are data structures. They're ways of keeping information. With stack, you push things on and pop them off, and the heap is the way to keep a large quantity of data and be able to get to it when you want to. The technical terms, local variables or automatic storage, and the free store. I say heap a lot, meaning the free store. So do an awful lot of C++ developers. It's actually the leftover C name, and many times the free store is implemented as a heap. It's not exactly wrong to use local and stack interchangeably, to use free store and heap interchangeably. It's a very common pattern among developers you're going to talk to. You may even meet a few guys who say, "Huh? Free store? What's that?" And you'll say, "The heap." And they'll say, "Oh, why didn't you say so?" You may run into sticklers who say, "What do you mean the heap? I believe you'll find it's the free store." You're like, "Okay, so I'm telling you both names." And technically the accurate name is the free store. That said, most developers say heap. Anyway, it's for longer lived variables. And there's an operator called new that sets aside some memory for you in the free store, and this operator returns a pointer to what has just been created for you up in the free store, the instance of a class, the object. It also calls the constructor for you, so it creates the object completely, sets aside the memory, runs its constructor. What you get back is a pointer to a fully constructed, happy, ready-to-go object. It will stay on the free store forever until you decide you don't want it anymore. And then you call delete on that pointer that you got back from new. And among other things, the destructor will run to clean up anything that the object has a hold of, and the memory will be released back to the free store to be used for other requests to new up an object. If you were creating what we call a raw array, if you want 100 integers, you want the memory for 100 integers continuously on the free store. The syntax is a little different for both the new and the delete. However, beginners should stay away from raw arrays and instead use collections from the standard library that we'll get to later. So using new and using delete are how you manage the lifetime of the objects that you create